So hello, today we are going to talk about a quick overview of some NLP models. So let's start with the goals of NLP. So according to different textbooks, there are different definitions for the NLP goals. For example, let the machines process and understand languages like humans do, and let the machines help humans better understand and use languages, and many others. And my favorite viewpoint is that NLP opens a window for automatic analysis of knowledge and intelligence. So I look at NLP as a window, and through this window, we can have a huge bunch of tools to understand and process the knowledge and intelligence in a way that we were not able to do without the help of the NLP models and computation power. So language is a window. We use the languages to learn, store, process, and convey the knowledge. It's like we think in languages. And it's debatable, though. Many people can claim that they actually think in images, but thinking in image and thinking in language are two very popular way of thinking. We can almost divide people into these two categories according to their mechanisms in thinking. So if someone is thinking in images, then the thoughts are more abstract and the idea is jumping around. But if someone is thinking in languages, then the ideas are more like connected, and it almost seems like that person can talk to himself or herself when thinking. And regardless, when we learn the knowledge or process or try to communicate between each other, we're using languages. And based on that, it almost feels like the category of people who are thinking in images has some implicit mechanism that conveys the language into the image and abstract signals. But regardless, people are still communicating in language. And another very interesting aspect is that humans can do so much by learning so little. So if you look back into the textbooks, what we have learned in the curriculums since primary school, middle school, and like university, there are only finite number of courses and textbooks, but we were able to combine the knowledges and use them, and of course forget a large portion of the knowledge, and yet we can still do so much. It almost seems like we can use the learned knowledge to do infinite things. So this comparison gives us the a question about what is knowledge. So a popular definition is the true justified belief, but this is very vague, you see, and it's debatable. To understand this, we can use language. You can use language to describe more clearly and give them a more clear definition than just the true justified belief. And many early NLP papers were written by cognitive psychology researchers, actually. So let's get to this question: how do humans know so much by learning so little? This was one of the Plato's question, and it was also an argument of productivity in the compositionality, but we will get to that later. And in previous frameworks, the Chomsky view proposes that there is a universal grammar that's common among languages. So language learners can unlearn these rules from the noisy input. So after the students learn these rules, they can naturally generalize to almost infinite future languages. So it's very easy to learn, very easy to do a lot of things after some certain rules has been learned. Or if we take a step further, maybe humans know some of these universal rules even since when they're very young. For example, if we say these universal rules are some categories like time, space, or even causality, or let's look at the numerical category. If humans know the difference between one and many, then it's it's relatively easy to map the noisy input, which are the text or the language that other people talk to them, and then they figure out that this corresponds to one, this corresponds to many, and this thing happened in the past, this thing happened in the future. So this would help them learn the under the rules fast and generalize in the future. But a counter argument towards this framework is the linguistic relativity or linguistic determinism. These are the Sapir-Whorf hypotheses. And currently, more people are in favor of the Sapir-Whorf hypothesis instead of the Chomsky view. And this hypothesis states that languages influence or even determine people's ways of thinking. So the arguments are subtle. There's an extent of the influence from the language to people's way of thinking. So instead of having a universal rules that is contained in these languages are different, and the different things among these languages can implicitly influence or even determine to some extent how people think. So these are the hypotheses. And there's another framework called compositionality. This is also a debatable framework. There are two versions of compositionality. A bottom-up one states that the sentence meaning is combined by the meaning of its different words. Or let's say in general, the meaning of a large, complex item is determined by a function, the composition function, and the meaning of its component. And there's also a top-down context principle. The top-down one states that the word meaning depends on where they are used. So if we think about the two versions, it feels like the bottom-up one and the top-down one almost feels like contradictory to each other. But either one of them can be supported by the productivity argument, which is we can learn, we can do so much by learning so little. There are more discussions at this blog, how to stop worrying about compositionality. And an interesting thing is that either of these two principles are very popularly attributed to the Gottlob Frege, but it seems like he believed in neither of these compositionality principles. And After that, there are some newer frameworks called semantic holism, which states that we can't just decide or assign some fixed meaning to the components and just use some fixed compositional functions to combine them. So the semantic holism is more like the top-down context principle. So what you mean depends on where you use and what's your goal for it. So personally, I'm more in the favor of the top-down one. And this is just because it feels like a more flexible framework, and this allows us to apply more of the neural network models to model this semantics and the pragmatics of this text.
Hi, sorry, I have a question. Can you go back to yeah. So for the bottom-up principle, how do they handle the ambiguity in word meanings?
Ambiguity in word meanings. I think they try to. There are two methods, I guess. One is to just pass in different arguments and say there are. So instead of passing a number for the words, they pass in several numbers for each word, and then they pass in some additional arguments into these functions. So the function can choose to like interpret this word into one of the several meanings as represented by the numbers. I think this almost feels like an LSTM. This almost feels like an LSTM. The composition function takes in different words as just the text, and this function assembles the meanings.
I see. Yeah, thanks.
Yeah. That there was a paper that tried to answer this question from a numerical point of view. So previously we were only talking about the abstract way. So we didn't go into the numerical way, and everything before that could only be done by just humans arguing against each other. So it's hard to apply them onto large corpus. But this paper is one of the early attempts by cognitive psychologists, and they proposed the latent semantic analysis theory to represent the semantics with low-dimensional vectors. And the low-dimensional vector is better than the raw text because they're computable, and it's possible to compare the semantic similarity using, for example, the cosine distance. So their way is basically a singular value decomposition. So they first construct a word context matrix, which is number of words by the number of contexts, and they specify the number of they call factor, which is the dimensions of the low-dimensional representations of the words. And they do an SVD and take the most the 300 most significant factors. So the resulting matrix A are the low-dimensional representations. The matrix A is number of words by D. So each word has a D-dimensional vector representation. So this approach is subject to the criticism that it's a static embedding. So it's basically each word has only one representation, and it cannot represent different meanings according to different contexts. So there are a lot of So there are a lot of approximations out there. But regardless, they can still do pretty well on the TOEFL synonym questions, which is to select the synonym word from the 4 candidates. They also experimented with different dimensions. It seems like around 300 is a good dimensions for getting a good performance on the synonym test. But the good performances are not very high. It's around 0.553 something. But considering that if you choose randomly one out of the 4, you will have 25% accuracy. So 53 is about a good performance, but it could be better. So an interesting aspect of that paper is that there are a lot of connections to neuroscience. The matrix multiplications are comparable to the message passing between axons and dendrites. The neural network models popularly used to simulate brain processes can be recast as matrix algebraic operations. Actually, in recent years, the NeurIPS conference actually has a section of the artificial neural network. It's not about the traditional deep neural networks that we are talking about. So that section of papers are just about the biological neural networks. They actually simulate the brain process as matrix algebraic operations. And also, let's get back to this paper. Also quoting from page 8, we of course intend no claim that the mind or brain actually computes an SVD or a perfectly remembered event by context matrix. So this is just models that the authors propose that is easy for the computers to do, and it can get good results on the semantic similarity task. So I think 6 years later, this paper came out. So can we compute the word vectors without doing SVD? And at that time, an alternative is just to use neural network, because different from SVD, a neural network can be optimized with backpropagation. But they need to set up a special supervised learning task for the neural network. And the supervised learning task they chose to do is the language modeling task, which is basically to predict the next word given the previous word. And the loss function is the perplexity, the exponents of the mean of negative loss, negative log likelihood loss. So it's on average how surprised the models is when seeing the next word, given that they have seen the previous words. So they evaluate with this perplexity on the testing set. So the benefit is that the neural network allows parallelization. So of course, SVD also can allow parallelization, but at SVD, but the neural network can allow us to incorporate prior knowledge. For example, if we pre-train the neural network with some other task, and then optimize on this language modeling task, then this can allow us to incorporate prior knowledge. And we can have the possibility to interpret or even use the word vectors. And the limitations is that these word vectors are still static. So the criticism for the static vectors are there and will be there all the way until the contextualized language models occur. And the next one is to use the word vectors. This is the traditional NLP pipeline. So they first compute the word vectors, and then they use these low dimensional word vectors for downstream tasks. And they found that this traditional NLP pipeline allows very, very good and flexible, very good performance and flexible pipelines for a wide variety of tasks, especially classification data sets. And also, by the way, if they want to adapt to multiple meanings of a word, they can just use the some models that compose different words into the models. For example, the infraset, that is the basically the LSTM. But in 2013, there are two, I think it's two models came out that they were very popular. And the first one is the word-to-vec. Word-to-vec was described in a series of papers by Mikolov et al. And I'm going to talk about two of the papers that introduces skipgram and continuous spec of words respectively. So skipgram sets up the task as given a word predicts its neighbors. Continuous spec of words is the reverse, given the neighbors predict the word. So these tasks are more interesting than the 2003 papers, which was just to predict the next word given the previous words. So the given a word predict its neighbors, or given the neighbors predict the word, allows more flexibility. And they use a two-layer fully connected neural network for this task. The first layer is projection. They project the vocabulary from they project from the vocabulary size to embedding dimension, and the layer 2 is project them back. So after that, the layer 1 and layer 2 are called the input and output embedding respectively. So we can take the layer 1 as the word embedding, and for the optimizations, they're training this network from the data, from the corpus itself. So given its corpus, it's possible to just find a lot of word and the neighbors, word and neighbors and word and non-neighbors pairs. So they take the word and neighbors as the positive data and the word and non-neighbor as the negative data. And this is the negative sampling. So after that, they can get the word-to-vec model. And this word-to-vec model has a promising linear analogy. So probably the most popular linear analogy is that the vector of king minus the vector of man plus the vector of woman is very similar to the vector of queen. And from figure 2 of that Mikolov 2013 paper, there is a very interesting linear analogies from this from the country to the capitals. So from each country to the capital city, the vector appears almost parallel when we project them onto a PCA dimension. So this looks like a promising linear analogy. And later we are going to explore more of the geometry of these word embeddings. So the next year, people have found that there have been two methods up to now. The global factorization methods, for example, latent semantic analysis, captures the corpus statistics very well, but that's pretty poor on the word analogy tasks. So only slightly above 50% accuracy was not satisfying. But they got the corpus statistics well because it was computed from a global matrix. But for the word-to-vec, the local context window methods were good on analogy tests, but they didn't capture the global statistical information because they were sampling from the word neighbors versus the word and non-neighbors data, and it didn't quite care about the global statistical information. And the goal of the author is to produce is to find a word embedding, and in this process produce the linear direction of meaning while utilizing the corpus statistics. So they are still using the neural network approach, but they want to design some tasks so that this task preserves the directions and also uses the corpus statistics. So they designed the loss function in a very smart manner, and the overall loss function is presented in this complicated equation. But it looks complicated, but it's not as complicated as it appears to be at the first sight. And I'm going to explain it step by step. So let's matrix X measure the word co-occurrence count, and the matrix X captures the global statistics of the word, the global statistics of the corpus. And the goal is to learn the word vectors W and W2 from the X matrix. So W are the word vectors that they are trying to optimize, and they propose, and they want to optimize this objective function. And the f of xij is an activation function that I'm not going to talk about that. It's the most important part is the latter part, the almost like a squared loss. And the intuition of the author is that this squared loss formulation preserves the linear directions of the word meaning. Why? This is because when the linear analogy of word meaning is preserved, J is minimized. And since the previous activation function part is almost positive, J is minimized when the latter part, the square loss part, is close to 0. So when the square loss part is minimized, the exponent of these two terms, which are the inner products of the two word vectors, are equaling the ratios of the co-occurrence matrix. So when they take the logarithm and add two bias terms, this becomes the square loss term. So what does this mean? This means that if words I and J are similar, then the inner products of these two matrices is large, then the word J should occur more frequently in word I's context. Remember that Xij is the occurrences of J in I's context, and Xi is all the words that are occurring in the in the ice context. So among all the words that occur in word ice context, if J occurs more frequently, then this ratio is going to be large. And according to the context principle, words I and J are very similar, and their inner product is large, and they add an exponential terms here, so the math will work out. So this is how they construct the Glovex objective. So by doing this, they're able to preserve both the global statistics and at the same time produce the linear directions of meaning. Later, the people have been using some neural networks to do the composition part. So the goal of a composition function is to assemble the meanings of different parts of the sentences together. So LSTM or CNN can work well to some extent. And in 2012, the matrix vector RNN is not recurrent neural network, it's recursive neural network, was specially designed to classify the semantic relationship and sentiment. And it was this kind of model design was really suitable for classifying the semantic relationships. It's like appending or inserting a not to the front of a phrase can negate the meaning. So this MVRM was really good in classifying this. And later, AWD LSTM was add some weight drops, and they trained with amortized SGD, and it performs really well in language modeling task. So until the BERT came out, AWD LSTM has been the state of the art for language modeling. So since neural networks can be used as composition functions, and this essentially solves the limitations in the static embedding, why don't we just use the neural representations as the word vectors? These are the contextualized word embeddings that can just produce context-dependent word representations for word meanings. So this is the intuition for the embedding from language models, the Elmo model. In 2018, LNAI proposed this model, the first pre-trained bidirectional LSTM. It's a character CNN and then 3-layer LSTM. And then combine all the layers into a single vector with some weighted averaging, and then add some regularization and dropouts, and then fine-tune on downstream tasks. So it's using both CNN and LSTM, and using both attention and recurrence is weird. So attentions are fast. LSTM seems almost like a redundant. So how about using only the attention part, but deeper networks? Considering that 1 year before a very popular paper came out, it's named "Attention is All You Need." So according to that paper, in the transformer model, using only the attentions could get almost as good performances as the carefully fine-tuned LSTMs. So why not just try using transformers instead of the LSTMs? It turns out that this results in BERT. So Devlin proposed this bidirectional encoder representations from transformers. This was a 12 or 14-layer transformer encoder. And the encoder is, we'll talk about the encoder here later. They use the bipair encoding tokenization, and also there are a lot of details in the model design. For example, they split the attention head into key query and vector and use Gaussian linear union activation. And they also train with different pre-training tasks like mask language modeling and next sentence prediction tasks. And this combination seems very arbitrary. And by the way, if we replace the encoder with a decoder, then this essentially goes into the GPT model by OpenAI. So the difference between encoder and decoder is that a transformer encoder connects both the tokens from the past and future, but a transformer decoder connects only the tokens from previous. So a transformer encoder can be used to encode because all the tags are provided, but a decoder can be used to decode in a sequence-to-sequence translation tasks, and where only the past were available. So this combination of the tricks seem very arbitrary. Like, why use some of the NLM tasks and some of the NSP tasks? Why are those tasks different? Recently, this paper did some systematic analysis on this pre-training losses. They considered many other pre-training tasks, including the token level tasks. For example, the regressions predicting the token's term frequency, and also some sentence level tasks, including the next sentence prediction, and also 6 ways to combine the tasks. For example, alternating this task in each iteration. And they found that next sentence prediction doesn't work as good as other tasks. It seems like because this is a shallow task compared to others, like predicting the terms frequency or just predict the token itself. So these are a brief summary about some methods for NLP and some motivations behind doing NLP. And for next week, we're going to do a quick review of some expandable AI methods. And after that, we are going to build upon the methods that we talked about this week and the next week, and we're going to dive in some topics. For example, analyzing the geometry and doing some behavioral testing. This will be some very specialized small topics that tries to tackle some specialized questions for in the interpretable and NLP region. Okay, thanks. I'm gonna stop the recording.